Given that f is an entire function satisfying this condition that f of z plus 1 equal to fz plus 1 and f of z plus I equal to fz plus I for all z belongs to C. We need to show that there exists a constant C such that fz equal to z plus C. So define zz equal to fz minus z. Then z of z plus 1 is f of z plus 1 plus z plus 1. By given condition it is same as f of z minus z, which is same as zz. Again, g of z plus I is f of z plus I minus z plus I, which is same as fz plus I minus z minus I, which is fz minus z cz. So then G is doubly periodic. On real axis its period is 1 and on imaginary axis its period is I. Okay, and since f is holomorphic, then G is also holomorphic. If f is holomorphic, then G is also holomorphic. And on C, that means G is entire. And G is doubly periodic. That means it is enough to fundamental domain means this is 1, this is I. You can take this one. You are taking this. This is I, this is 1. So since it is doubly periodic, that means f of z plus 1 is same as fz and f of z plus I is same as f. So that means it is enough to check the image of this. So image of G same as G on C same as image of G on this, right? Now G is continuous on compact set implies G is bounded, right? And image of G on C is also same as the image of this, right? That means it is bounded entire. This theorem, G is constant. Fz minus z is constant, so fz equal to z plus c. So this one is easy one. Another one problem. Show that there is no continuous function f on D bar such that f is holomorphic on D and fz is z bar, right? Okay. So this is your domain D, right? And f is holomorphic inside this, and f is continuous on its boundary, right? See, if you take any loop here, say mod z equal to r, where 0 less than r less than 1, take this, then f is holomorphic inside that domain, right? So will imply from given condition f is holomorphic in mod z less than r, right? That means integral on the boundary of the domain mod z equal to r is integral mod z equal to r f integral mod z equal to r f is basically 0, because f is holomorphic inside this domain and the domain is connected. So this integral is 0 by Cauchy-Bouchard theorem, right? By Cauchy-Bouchard theorem. Now f is holomorphic, right? F is holomorphic and f is also continuous. Then r tends to 1 implies integral mod z equal to r tends to integral mod z equal to 1f, right? And since for every r less than 1 mod integral is 0, that will imply integral mod z equal to 1 f is 0, right? But given that fz equal to z bar 0 to 2 pi d theta, which is same as 2 pi I, which is not equal to 0. That's a contradiction. Okay, so hence there is no continuous function that satisfies this. So you are basically taking that domain disk and you are just taking a small enough loop inside that, and you know that f is holomorphic inside that domain, so that means by Cauchy-Bouchard theorem this is 0. But when you approaches to it to mod z equal to 1, and each stage integral is vanishes, but on boundary limiting sense, when you are checking that, then mod z equal to 1, the integral doesn't vanish, it becomes 2 pi. So that means it's not there is no such function satisfying this condition. Okay, thank you.